Hello, thank you for being here. I'm Rewkowski, and I am presenting Evaluating the Effectiveness of Redirected Walking with Auditory Distractors for Navigations in Virtual Environments. Quite a title. So, to give some background, I will discuss the following topics. So, there are many virtual locomotion interfaces. There's gamepad movements, walking in place, teleportation, there's motion compression, and what we are focusing on is redirected walking. We zoom in on a very specific topic of redirected walking, which is unfortunately a pretty small field, which is auditory redirected walking. And we also employ the use of distractors as proposed by Tabitha Peck, and I will explain more in a bit. So as with any other redirected walking paper, our goal is to achieve real walking in VR with limited physical space. And the field is massive. There are a huge number of methods and studies that prove what works, what doesn't. From the original paper to papers like change blindness, all the way to recent papers like saccadic redirection. So we try to tap into this wealth of knowledge as much as possible when we design the study that I will discuss. So we focus on auditory redirected walking. It's a very small field. There's a paper on the detection thresholds, which they find is we should use a rotational distortion of about 20% as opposed to 30% like with vision. And there are some applications papers, but overall we don't find any papers that prove that auditory redirected walking is possible in more practical situations, such as training a blind person across a street, for example. So what we want to do is design a virtual locomotion interface for audio-only groups. In this paper, we define audio-only as a group that doesn't have any visual cues whatsoever. So think of a completely blind person. Vision-only would be somebody with no audio cues, so a completely deaf person. And our audio-visual group is essentially the control group that has all possible cues. We would like to train audio-only users to complete tasks in commercial VR setups like the HTC Vive using redirected walking. We would like to do so with audio distractors without noticeably distorting the audio field. And our ultimate goal is to achieve auditory redirected walking with a high sense of presence. So in our work, we demonstrate that redirected walking with distraction does in fact allow audio-only users to complete navigational tasks. We are, to our knowledge, the first study that directly compares the performance of audio-only, visual-only, and audio-visual groups under otherwise same conditions. And we prove that audio-only, distraction-based redirected walking can in fact be imperceptible and evoke a high sense of presence. So we performed 2 user studies, the first of which is a between-group study in which we directly compare the 3 groups that I mentioned. And the second study was an exploratory single group study in which we tried to push the limits of auditory redirected walking. So to quickly go over the evaluation system, we have this steer to sensor redirection that is constantly enabled. We use a rotational distortion of 15% of head rotation, which is a little bit under the finding of 20% because we didn't know how the 20% would fare with distractors. We didn't want to be overly ambitious. And we also achieve reorientation with a distractor. We choose whether or not to activate the distractor by testing the user's trajectory against an elliptic boundary. We use an elliptic boundary so that they don't collide with equipment that's in the corners. I will explain in the next slide what these normal and reset distractors are, but we initially employ a normal distractor if the user is about to leave bounds. And if the normal distractor keeps failing, we use a reset distractor. It's fairly standard. And so our normal distractor moves from the goal towards the direction where the user should rotate. And it moves kind of towards the center of the physical tracking space in an approximately parabolic path. And it does this once, and it goes back, and the user's rotation kind of moves so that they're facing the center of the space. If this keeps failing, we use a reset distractor, which moves from left to right 3 times. And ideally, the user will be facing directly into the center of the tracking space. And this is essentially a fail-safe. In the video, you can see the normal distractor, which moves towards the user's left because that's where we ideally want to turn them. So in the first study, we have some training and intermediate scenes, which I will explain later. And then we have 3 main scenarios that we study. The first one is a living room. The second one is the Firedrill scenario from the original redirected walking paper. And the third is a complex traffic crossing simulator. So the first of the training scenes is meant to introduce the user to walking in VR, and they also are introduced to their hands, which are tracked by elite motion. And they use these to complete simulator sickness questionnaires and to wave at the distractor, which is what they're told to do. We did this because we didn't want to make any assumptions about, I wish my video would play. We didn't want to make any assumptions about how comfortable the user was in VR. The second training scene introduces them to the distractor. They're taught to look at the distractor and wave to it whenever they think it's active. For audio-only users, they can hear this dog panting noise. For visual users, they can see this little arbitrary point system called robot happiness points, and they use that to tell whether or not they're doing everything correctly. Our intermediate scenes play between all of the levels. They have two purposes. The first is to complete a simulator sickness questionnaire on some virtual TV. And they're also introduced to the next level and its structure, which is especially important for audio-only users because they won't be able to see anything. So they'll have trouble figuring out what they're supposed to do. And keep in mind that these audio-only users are simulated blind. So they're essentially users that are not actually blind, but their display is just cut off. So our first level is a living room. On the left, you can see a legend that tells you what each of the variables in our figures mean. And in this study, the user walks from one side of this living room to the other, and they're approaching a big green question mark goal. And the only dynamic audio and visual sources are the goal itself and the distractor, and there's a reverberation filter applied. So it's a very, very simple scene. The second scene is the Firedrill scenario from the original paper. And in this scene, the user, they move between 5 buttons, and they need to hit them in order. The original paper did not, it didn't have a cue that shows them which button they should be heading to at any given point. We need to use a question mark because in the absence of vision or audio, it would be very difficult to tell which button you should be heading to. And the third scenario is a traffic crossing simulator. It's a very complicated scene. There are vehicle sources. We specifically chose vehicles that have really annoying sounds like police cars and motorcycles. And there are pedestrians that walk along the sidewalk and randomly decide whether or not to cross a virtual street. And the pedestrians are especially meant to help with the audio-only users so that they can tell whether or not they're actually in the crosswalk. And there is a beeper on each side of the street that makes a different noise. In the intermediate scene, before the level, the user is told which source applies to which side of the street, and any position on the other side of the street is considered successful. So it's a very complicated scene. In this first study, we had 43 participants, 20 females, 23 males, with an average age of 23. About half of them had a decent amount of VR experience, which, as we'll see, did not seem to make much of a difference. We collect the following data. We collect what we call performance metrics in each level, which include the number of normal and reset distractors, the time to complete each level, what we define as the distraction ratio, which is the percentage of the completion time during which the distractor is active, and their average walk speed. Then, throughout the entire study, we collect what we call experience quality metrics, which include simulator sickness, perception of distortion, which we use a custom questionnaire for because this is a very small field. We didn't quite have any resources that we assumed would work well enough. And we measure sense of presence. We measure sense of presence with a standard Slater-Russo-Steed presence questionnaire. So as to not bore you with the statistics, I will summarize our findings. We found that the two groups that had vision performed similarly in all regards. The audio group walked slower, and thus we find this correlated to a lower distraction ratio. So they walked slower, the distractor was active less of the time. The experience quality, surprisingly, was pretty much the same between all groups, which we found surprising, especially because the users had simulated blindness. So this was very surprising. We did not find any significant interaction between the level or task and the modality. So to some extent, we can generalize our results to other types of tasks. And finally, we find that the gender and level of VR experience was actually not significant at all. So our second study was exploratory. We wanted to see if we could do obstacle avoidance with audio redirected walking, we add an obstacle avoidance module to our system, which creates generous boundaries around an obstacle, in this case a couch. And when the user approaches the boundary, a temporary goal location, which is G of T, it is calculated to be in a position that they can reach without running into the obstacle. The scene itself is more or less the same as level 1, except we added furniture like couches, chairs, and tables. And here you can see 3 example paths. Since there was only 1 user group and 1 scenario, we only had 14 users, and none of them were in study 1. We don't report any other demographic information because we're not comparing the groups directly, and it was exploratory. And because it was exploratory and we only wanted to know if it would work, we only focus on these performance metrics, how many obstacles they actually hit, and how many were avoided successfully, as in a temporary goal location was created, they walked towards it, and they intentionally avoided the obstacle. So we had 2 main findings. The first is that our obstacle avoidance module works 2/3 of the time, which we were quite happy with because it's not particularly optimized. These were some example paths. And our main takeaway is that complex navigational tasks are actually possible for audio-only groups, which is very promising for example, blind users. So to discuss these results, we conclude that audio-only navigation with distractors is in fact feasible. The audio-only distractors do not cause any more simulator sickness than normal distractors, or I mean visual distractors. Through observation, we believe that reorientation would work better for audio-only groups. The reason we say this is because we notice that the blind users like to plant their feet, choose a target, and walk straight there without rotating their head. So redirection tended to be less effective for them. We don't know if that would be true for blind users because they are a little bit different, but I'll talk about that later. We reconfirm previous results that walking slower increases the quality of the redirection, because if they're not running out of bounds, then they don't need to be distracted as much. The audio-only group, which we call Group A, is susceptible to sensory overload, especially in the traffic scene, which has so many audio sources. It took them much longer than the groups with vision to figure out what they were supposed to be doing and to localize all the audio sources and to create a mental map of the space. So this was very difficult for this group specifically. We find that the 15% rotational distortion was a bit too low, and it wasn't particularly beneficial to keep it so low. So we would recommend 20% or higher, which is what previous studies found. And finally, we want to note that we cannot generalize these results to actually blind users because they have other abilities, like they're better at mental mapping and so on. And we don't want to generalize to more serious tasks because, for example, you wouldn't want a robotic dog running around your hospital. In terms of future work, we would like to redo the study with actually blind participants. This would be a great next step, possibly with a higher rotational distortion. We would like to further analyze this preference for reorientation versus redirection. We could, of course, improve our obstacle avoidance algorithm, which right now was very greedy. And finally, we can use more realistic distractors, for example, haptic distractors. So maybe we can represent the cane that they use or a guide dog, or maybe we can even represent tapping on a shoulder or something like that for blind users. Also, we could use a custom HRTF to make an audio distractor sound more realistic to them. And there are many other ways that we could use more realistic distractors. So that is the end of my talk. These are the I would like to acknowledge these funding sources, the NSF and the ERI Chair Professorship. And that's the end of my talk. You can find more information at our website, assuming it's up right now. Thank you very much.
So we're running a little bit over time, but I think it's in the best interest to have questions.
So very, very quickly, very nice work. One thing that I was thinking is combining audio redirection with just regular virtual environments rather than just audio-only navigation. So in order to not interfere with a visual task, to use audio for redirection instead of a visual distractor. Have you thought of that, and what are your thoughts of?
In a way, we did do that because we didn't design our levels specifically for the audio-only users. They were designed so that nothing would change between the user groups. So the visual-only group, for example, could still complete the level. The audio-visual group that has all of the cues, they're still I mean, everything is consistent between the groups.
But I mean, having the visual only with audio only redirection without the dog that you see.
Oh, I see. So our work heavily extended Peck's work, Tabitha Peck's, and she used an audio only distractor like I think it was a butterfly, and moved back and forth really quickly. And the goal of our dog was to make that kind of thing more realistic. So I see what you're saying. And the reason that we used a dog was mostly to increase a sense of presence. We didn't want to make it obvious that we were doing redirection. And that's why we went this way.
Okay, thanks.
Yeah.